So in this session, we'll look at the topic CPU scheduling. Basic concept of CPU scheduling arises from the concept of multiprogramming. We have multiple programs loaded in the main memory, and these multiple programs will be executed in concurrent manner in the CPU, right? So the next question arises is which program will be executed and when. So to decide the order of execution of these multiple programs from the main memory, we have to schedule them, right? And this scheduling procedure is called as CPU scheduling. So to maximize CPU utilization obtained with multiprogramming, we have to order these multiple programs so that they can be executed in the CPU concurrently, right? So a program may have some CPU instructions, it may have some IO instructions. Like if we have an example, so say we have this one, int main, int a, fp pointer is equal to, which is of type file, f open abc.txt, and we open this file in write mode, right? And then we write something into this file, say fwrite, hello. So this instruction, or we are writing hello to this abc.txt file, and then printf hello is written, and then return 0, right? So in this program, int a is a CPU burst, it requires the CPU. File fp pointer equal to f open abc.txt in write mode. So when this instruction will be executed, there is a need to open a file, or there is a need to create a file in the secondary storage if abc.txt is not already present. If it is there, then this file has to open from secondary storage. So some IO operation regarding secondary storage will be required at this particular instruction. So this is, you can say, this is CPU instruction, and this one is IO instruction, and again this one is the IO instruction, because we have to write this string into this file, and that file is present at the secondary storage, right? So again this is the IO instruction, because we need to display this content on the monitor. So at this time, monitor is our IO device which is required. So you can say that CPU, then again IO, then IO, then IO, and then some CPU instruction is there in this program. So we can say that this program is alternate sequence of CPU, IO, 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 and CPU instructions. So a program may contain some CPU instructions and some IO instructions, and these CPU and IO instructions can be executed in interleaved manner, right? The order of these instructions is not defined, it totally depends on the type of program which you have written, right? So the concept here is to understand is that a program may have some CPU cycles or IO cycles, right? So when a program is executing in the IO, if I have another program in the main memory, I can shift that program into CPU when another process is executing its IO, so that maximum utilization of CPU can be achieved. So this can be the overall structure of any program where alternating sequence of CPU and IO bursts are required. So load, store, add, store, read from file, these are the CPU instructions. Then wait for some IO, then some increment, index, write to file, again some IO instructions are required, then some CPU instructions are required, then some IO instructions are required, and so on. So this can be the overall skeleton of any program. So a CPU scheduler selects a process from the processes in the main memory that are ready to execute and allocates the CPU to it, right? So we have multiple processes or multiple programs in the main memory, and from those programs, CPU scheduler is going to pick up one process that will be executed in the CPU next. Load it into the CPU. So CPU scheduler job is to just pick up or just to select a process from the main memory that this process will has to execute next. Now CPU scheduler job is done, and then dispatcher will take this process from main memory and load it into the CPU. This means dispatcher will load the contents of PCB into the CPU registers, right? So dispatcher involves context switching. Context switching means the contents of CPU registers for the running process will be saved back to main memory first, and then the contents of main memory of the next process which is going to be executed in the CPU will be loaded into the registers of the CPU, right? And then the CPU's mode will be switched to user mode by default mode, and then jumping to the proper location in the user program to restart that program according to the program counter. That what was the last value of program counter, from there only the next scheduled process will be executed or resumed, you can say. So dispatch latency is the time it takes to the dispatcher to stop one process and start another running process, right? So stopping a process means saving the CPU register values into the PCB of that process in the main memory, and then loading the contents of PCB of the next process into the CPU registers, and then changing the CPU mode to the user mode. So this time duration is called as dispatch latency. The time a dispatcher takes to change the process in the CPU. So scheduling criteria may be CPU utilization, turnaround time, waiting time, and response time. So this means whenever we try to develop any scheduling policy, what all parameters we have to consider, right? Our main purpose is to maximize the utilization of the resources, and in this case we are trying to maximize the utilization of the CPU. So CPU utilization has to be maximized. Number one, that means keep the CPU as busy as possible. Throughput is number of processes that complete their execution per unit time, right? So throughput is another parameter which we have to consider. Turnaround time, it is the amount of time to execute a particular process, that is the summation to termination duration. So when a process is submitted to the system and when it is finished, the time duration between these two events is called as turnaround time of that process. So again, the arrival time of that process and when it is leaving from the system. So time duration between these two events, arrival and completion, is called as the turnaround time of that process. Suppose a process P1 is submitted at time 1 second and it is finished at 10th second. So turnaround time for this process is 9 seconds, right? Waiting time, it is the amount of time a process has been waiting in the ready queue, or it is the time when a process is doing nothing, right? When a process is executing some IO device, we cannot say that this process is waiting, because at that time the process is actually busy in doing some IO task. So that process is not waiting for some resource. So waiting time actually is the time when a process is waiting to be executed either in the CPU or for some IO computation, right? So a process is in ready queue which is actually waiting for some resource is called as its waiting time. Suppose a process is waiting for some IO device, then again that waiting time will be included in the waiting time of that process, right? But when a process is executing in the IO or it is busy to execute the IO, we cannot say that process is waiting at that time, right? Response time, amount of time it takes from when a request was submitted until the first response is produced, not the output, right? So when a process is submitted and when it is getting the first response, so this duration is called as its response time. Suppose a process is submitted at time 1 second and its first response is coming at time 5 second. Response means when this process is getting the CPU. So that duration is called as its response time. So optimization criteria for any scheduling policy can be maximizing the CPU utilization, maximizing the throughput, minimizing the turnaround time, because turnaround time is the time duration between submission of an process to the system and till the completion of the process. So we want to complete our processes as early as possible. So if process is finished as early as possible, its turnaround time is obviously minimized. Minimum waiting time, right? And minimum response time. So to optimize any scheduling criteria, these are the parameters we have to consider.